where can this? Where? Hmm? Hmm? Why doesn't this work anymore? Oh. Okay, this should be fine. Okay, any question from last time? Last time we go through this Shor's factoring algorithm, everything. Okay, so let's start with a short review. So from last time we know how to do phase estimation. Then we use phase estimation to give factoring algorithm. And the core part of the Shor's factoring algorithm is this order finding problem. It is that so you are basically want to factor this big N, and well, the way you do this is you are given you are going to select on random x that's smaller than n but coprime to n, and you want to find this order r of x respect to n. And this order r is defined by the smallest integer such that x to the r equal to 1 mod n. Okay. So x to the r is some multiple of n. And this is pretty hard for classical computer because basically don't know anything any smarter way to do this. You just keep multiplying x to find this, and yeah, you just keep multiplying x and doing mod n until you hit this x to r. But r can be very big. R can be something like order n, and then you need to do a lot of multiplication, and that takes a lot of time. But we see that there is a quantum algorithm that only use that gives the exponential speed up over the stupid way to do this. That is, so that's the quantum order finding algorithm, and that's where you use phase estimation. And here L is basically log n. Okay. So you only need polylog n number of steps in a quantum computer to find this period r. And the quantum phase is the quantum order finding algorithm basically is phase estimation to multiplication, where we define this multiplication unitary. It's very classical. It maps the computational state to another computational state. So if you give the computational state that corresponds to the integer, and this ux is related to this x, where the order you want to find. So you do this ux acting on y, then that just give you xy, and everything is modern because yeah. Okay. And we show that you can just do phase estimation on this unitary, and with the eigenstate, well, not quite eigenstate, but on the phase estimation state of being 1, then you can find some s over r with the uniform random s. That's because when you consider the eigenvector that corresponds to this space of things 1 getting multiplied by x, so like 1 x squared all the way to x to the r, this r-dimensional space, then its eigenvectors are like this. So it's equal superposition of all those x to some power, and times some exponential phase. So the phase is basically rth root of 1. And so those are eigenvectors, and more importantly, their eigenvalues are this exponential 2 pi s over r, with s from 0 to r minus 1. Okay. So and they are hard to find, but 1 is a uniform superposition of those eigenvectors. So if you do phase estimation on 1, then basically you are doing a phase estimation on random one of them because it's equal weight superposition. So you are drawing every S with 1 over R probability, and once you get S, and if you draw another S, then you'll get the corresponding phase, which is S over R. So you will get S over R, and you can calculate R from this if you draw enough of them. And we see that there are several problems. So you need to do the multiplication very efficiently, and we see that you can do that by just repeated squaring. And and also S over R might not be like a binary string, so binary fraction, so there will be some error, and we see that you can use continuous fraction to get rid of that. And then S over R, S and R might not be coprime to each other, but we show that you just draw a whole bunch of different S and take the this common multiplier to all the R you see, then you have a pretty good probability to get this correct. Yeah. So that's how you do order finding, and skip all those proofs. This is continuous fraction. You keep expanding out, and and prove that if you just do 2 of those S over R, you have a constant probability. So you just need to do log number of those. You will get probably log 1 ripson of those, and do some amplification. Then you can get the correct R with the epsilon probability. And you probably show this in homework, where you have this 3 over 4. And finally, we have the factoring. So what we have been talking about is order finding. Then let's see, we need to show that how you do factoring by using order finding. And just as we say, we're just starting with picking random x, the coprime to n. And we'll find the order of x. So this R such that x of R, x to R equal to 1. Then we need to place several things just by chance. So first R needs to be even. Okay? If R is odd, you just draw another x. There is another, draw another x. So if R is even, R is odd, you draw another x. If R is even, then you compute R over 2. And then you try to see this xr over 2. Then you know this xr over 2 squared equal to 1. So xr over 2 minus 1 and xr over 2 plus 1 equal to 0 modern. Then there are several cases. If xr x to the r over 2 minus 1, yeah. So if x to the r over 2, I should say this way, right? So if x r over 2 plus 1 is 0 modern, then this is another bad case, and you just draw another x once again. And if it's not, then we show that this xr over 2 minus 1 and xr plus 2 or xr over 2 plus 1, they will contain some non-trivial factor of n. So if we think n equal to pq, then they either have this as p, this is q, or this is q, this is p. And anyway, so you can just take this xr over 2 minus 1 and n, and then take the greatest common divider. So this should be Euclidean algorithm. Okay, Euclid's algorithm, sorry. Euclid. So there was a small mistake. Euclid's algorithm. And anyway, so if you are lucky here, this xr over 2 minus 1 plus minus 1, they both contain non-trivial vector to n, and you can just take GCD. And you will get a non-trivial vector p over q. And here we have yet another number 3. We won't go into detail, saying that this is constant probability, this best case is constant probability, and this best case is constant probability. So you just need to draw constant number of x to get a good x with constant probability. Okay. And any question so far? If not, then let's have a total summary. So total summary of the factoring algorithm. And so the first thing you do is you check, well, n is not an even number. If n is an even number, then you say 2 is a factor. And this is because the other part, which we didn't check too much. But anyway, so first you check n is not an even number. Then, because we need to use this, so and then you check that n is not just some prime to some power, because here you need more than 2 prime. So yeah, and that can be done by just keep taking the square root and the cubic root, etc. of n, and if you work out the details, this also only take order L cube calculation. Where remember L is log n. L is about log n. Okay. Then we start with our random picking of x. Okay, so we pick a random x from 1 to n minus 1. And first you check whether x contains any non-trivial vector of n. So you just, here is wrong again, Euclid's algorithm. Euclid's algorithm. Yeah, so you calculate the greatest common divisor between x and n. And well, if it's not 1, then you already find the non-trivial factor, you are happy. And if x and n are actually co-prime, then you can start trying to find the period of x. Okay. Okay. So up to here, we have to make sure that n is odd and has more than 1 prime factor, and x is co-prime to n. Just because we do all the checking. Then here we can use the order finding algorithm. So use the order finding algorithm to find R, such that x to the R equal to 1, modern, as we have been saying. And then we start doing our chance. So if R is, so if we are lucky, so what we need is R is even, so we can calculate R x to the R over 2. And we also need x to the R over 2 not equal to minus 1 modern. So those are the 2 things we just need to pass by chance. So, and we already say that, we already argue that up here, this thing. So if both of those things pass, we can find a non-trivial vector of n by just doing GCD of x to the R over 2 minus 1 and n. Otherwise, and then we are unlucky, then we just go back and try another x. And we say this will happen with constant probability. Constant probability. So, be the t. So this happen with constant probability, so this go back only need to happen with constant probability. Okay. And yeah, so just as we said, you only need to do this while loop constant number of times to pass this. Well, at least with a good probability. So, any question? No? No? So this is Shor's factoring algorithm, and that's basically a review. And now we want to go to here. So we have extra things. So we want to see Shor's factoring algorithm in another view. That's I guess I give you more intuition on Fourier transform, and also it's more similar to how we did Simon's algorithm. And so it's Shor's algorithm in another view. But we are focusing on the period finding part because all other parts are classical, right? And that doesn't really change, okay? So Shor's period finding. Period finding algorithm, okay? And okay, so let's go back to the start of class. What is Shor's period finding algorithm? As we said, it phase estimation, the unitary gate being this multiplication ux, and with the eigenstate slot, we are putting the number 1, okay? And let's just write all the phase estimation algorithm. So this is similar to what we had for phase estimation. You have some t-bits here for the record register, and then you do a head map to a t to make this into equal superposition here. And on the eigenstate register, we put 1 here. Then we do this t-bit control our unitary, right? And our unitary is multiplication by x. And so whatever j here, you will do multiplication j times, like it's actually j here. Okay? And our phase estimation, then we do QFT minus 1, and then we do measurement, and you will get some result. Okay? So here you should get S over R, because that's what happened in our previous analysis with some uniform random S. Okay? And now we are basically trying to analyze this in different steps. Okay? So what we are going to do is we will add a measurement here. So this is very similar to Simon's. We are using the fact that you can measure any qubit level alone, right? Because these qubits and these qubits are not interacting anymore. So what you do here shouldn't really matter here. So what about we just measure the result here? And so this is something you do that doesn't really change the algorithm output, but it makes so you don't really need to do this when you actually run a circuit. But this is a good way to make the analysis of our algorithm easier, because we cut down a lot of complexity, as you will see, and as we have seen in Simon's algorithm. Okay. Okay. So well, then let's start our math. So these should be things that I can ask question. So let's do this step by step. So first, let's see what happened before we apply the unitary, just as a small review. And as we said, so the second register doesn't really get changed anything. It's just equal superposition of every bit string. And then we relabel the bit string into the decimal number from some 0 to n minus 1. Here n is like 2 to the t. Okay? So, and k is just some dummy, so sum of this k from 0 to n minus 1. Nothing really happened, then we have normalization, 1 over square root that. And then we need to think a little about what happened here, but it should be easy. So you apply this t-bit control ux on the second register. Okay? And so now is where things get a little different. So previously we analyzed this by just decompose this into eigenvectors. But now we skip the decomposing into eigenvector part. We just think about what happened here. So you apply the multiplication on the second register. Well, you are basically multiplying 1 to 1 with x, right? So you are, because that's what this unitary do, is multiplying something with x. Well, you multiply 1 with x, it's going to be x, and you multiply 1 with x squared, it's going to be x squared, etc. So basically you are just going to get x to the kth power here, right? You want to follow? So you have k here, and then you will do this multiply x k times, so that's just x to the kth power. So that's a state we get after we after we apply this. Okay. And now we need to think a little carefully before we do the measurement here. So what is this x to the k actually is? Remember x to the k, they are not all different, right? Because remember our x is a period. We have a period such as x to the r equal to 1, right? So this thing is actually is periodic. That's why we say period finding. And so if we list all, you're going to be 1x squared, x cubed, etc. all the way to x to the r minus 1, and then x to the r will equal to 1. And so remember everything here is modern. Right. So this x to xr equal to 1 is just saying on this one. And then we have x squared, etc. So it's going to be cycling through those r different values. Right? So we only have those r values on this register. Okay? So that's the important part. And now we want to see what happens when you measure this. So we already know there are only r values. So when you measure this, it's going to give you one of those r values. Right? And now we do extra assumption that it's just because we want the calculation to be easier. Okay. So we assume that n is a constant, is an integer multiple of r, or r divides n. Okay. So it will make our notation a lot easier. So assume this, and yeah, and then we will measure the second register. Then we know we'll get one of those values, so let's just say those k. Right. So we'll get a random k from 0 to r minus 1. Okay, so we'll get these on second register, so tensor k, tensor, so on second register we'll get some, wait, why can't I? Okay. Some x to the k, right? X to the k. On second register, we'll get some x to the k with this uniformly random k. And now the quadrant is what's on the first register. So we'll project back into the first register that tensor together with x to the k. And that will be basically this, right? K and k plus r and k plus 2r, etc. Because, for example, say k equal to 0. So you are measuring this 1, then you are project back into whatever k that will give you xk to the k equal to 1. So we'll get this 1 and this x to the r equal to 1. So r is also another thing that give you 1 here, right? And we will get another 2r here, right? X to the 2r also equal to 1, right? So doing this measurement, we will I guess collapse. I should say collapse. So you do this measurement on the second register. You will collapse the first register into something very structured. You are going to get whole bunch of computational basis state that has this exact period, right? You see that all of them are going to differ by r, right? So it's different by r, it's different by r, because you have this period r. Okay. So here is the hard part. Everyone follow this projection or collapsing? Okay. So if we are good here, then these are values. Okay. Let us look at this. So this is the state we get. So once again, you will have a uniform random starting point k from 0 to r minus 1, and then you have next day is k plus r, the next day is k plus 2r, etc. All the way to, if you think carefully, it should be k plus n minus r. And the total number here, so that's why we assume this to make this much simpler. And so the total number here should be, well, every r state will get one state. So the total number of states is n over r. So the normalization here should be square root r over n. Okay? The number of states equal to n over r. And so let's go back. Then the next thing we do is we are going to do a QFT or QFT minus 1 on this. Doesn't really matter because it's real. So now we can kind of see why QFT work here if you know QFT. Because this is what's called the post-trend, right? So if you kind of draw the amplitude of this thing, right? Line is going to be, so you have some amplitude at k, and some amplitude at k plus r, and some amplitude at k plus 2r, etc. Right? So this kind of signal, so if you study signal in the process system, so this kind of signal where you have just pulses at equally spacing out place and with equal height, this is called post-trend. And it's very well known that if you do a Fourier transform on post-trend, it's going to be another post-trend, okay? So if you do QFT, then a post-trend becomes another post-trend. But so the spacing here is r, and that is going to be reflected to the transformed post-trend. So if the spacing is r there, then the spacing will be, well, it might be some constant, but it's going to be like 1 over r. Okay? There might be some constant depending on how you normalize your Fourier transform. But the point is, if this spacing is bigger, then it's going to be proportionally smaller upon Fourier transform. Okay. And okay, so that's how we're going to show rigorously. So we are starting with this post-trend state. We're going to do Fourier transform, and then we get another post-trend state. And because this spacing is okay, it's a little different. And the spacing is 1 over r here, and also it started with 0, just because kind of lucky. And then if we measure here, then this is where we get the s over r, right? Because the spacing is 1 over r. And so those are basically the s over r. So things that's s over r. That's how we get r out of this with the quantum Fourier transform. Because you see, if you just measure this state in computational basis, that doesn't give us anything. This is basically uniform random, right? Because that's where quantum measurement collapsing state makes annoying. So if you get 2 copies of this state, right? If you get 2 copies, then you can get say k and k plus 2r. then you can take a difference, and you know what's 2R, etc. But the annoying thing is you only get one copy of this. So you will measure this, then you get a random k and plus a random r, and then if you run this again, you will get another k prime. But the k and the k prime don't relate to each other, so you cannot really get out all those computational basis measurement. And that's why we need to do this Fourier transform to actually get this 1/r. Okay. So that's on aside. But let's see how the Fourier transform actually work. Okay. So the Fourier transform. So we start with this state. Let's write this in something more clean. So we give another dumb variable L, just saying how many R we add here. So this is square root 1/r, square root R over n, and the summation L from 0 to n over R minus 1. Excuse me. Wait, is this correct? Yeah. So this one is actually k plus n minus r. So L from 0 to n over r minus 1. So number of L is n over r as we expected, and k plus L times r. Okay. So we're just rewriting this into more compact formula. Then we basically need to do math. It's not too bad. So we need to do QFT minus 1. And so we just do our favorite formula. The formula where we see a computational basis state and we know what is QFT or QFT minus 1. So this state should get turned into summation another computational basis. And this is actually QFT1 on n. Okay, so we should say that. So QFT 2 to the t equal to n. So QFT minus 1 on this, then this thing should turn equal to this part. So you summation another dumb variable, which we call j. So j from 0 to n minus 1 as always. And e to the, now it is minus 2 pi because we are doing QFT minus 1. E to the minus 2 pi, then n over j and whatever here, right? So k plus AOR. And all other thing we just copy here. Okay? So this part is just brute force math. We plug in the QFT minus 1 formula. Then we do the thing that you probably expected to do, that is switching the summation order. Okay? So we switch to the summation order. Then we look at, okay, so what things are actually depend on L? Only thing dependent on L is here, right? So we can just take all the non-L part. So we have another e to the minus 2 pi I jk over n. This part we don't actually care, it's on phase. Okay. And so the actual part we care about is how the remainder things depend on L. Okay? Because we want to sum over L from 0 to n minus r over 1. And so here we have everything e to the 2 pi I. And we have a JL, we have a JL R over N. But we are going to group things together in this better way. So we have an R up here, but we move it downside and we are dividing N with this R. Okay? So JL over this N over R. So why we want to do this? Because you are grouping this N over R together or something. Okay, so we should probably do this earlier. Okay. So this over R, we are calling this n prime, and there is a number of terms here. Okay, and it's an integer because we are assuming that it's an integer to make things nicer. So if it's an integer, then things are quite easy. If you are rewriting n over R as n prime, then this is summation L from 0 to n prime minus 1, and now this is also n prime, e to the minus 2 pi j over n prime. But we've seen this kind of thing, right? This is the Fourier cancellation formula we've seen a whole bunch of time, right? If you think about n equal to n prime, then this thing we know that it's going to be 0 if so L is single sum over, so it's going to be 0 if J is not 0. And if J equal to 0, obviously this is going to be 1 summed over n prime times. So it's going to be n prime if J is 0, well, mod n prime. And if J not equal to 0 mod n prime, then it's going to get QFT equals spacing cancellation again, right? So this is the identity we have to keep seeing. And okay, so this part is this. Then now we think about what happened if you measure this register, right? This is what's going to happen because we're at the end of algorithm. We've done our QFT -1 and we want to do computational basis measurement. So what J actually have amplitude and how much amplitude is it? Well, we know J doesn't have amplitude if it's not some constant multiple of n prime, right? Because of this relationship. Okay? So if J not equal to 0 mod n prime, just has 0 amplitude because this part becomes 0. Okay? And for other so all the J have amplitude will have this form. It should have constant multiple. So the constant now we call S because this is what the matching notation from previously. So some integer S multiple of n prime, and now we give back n prime equal to n over r. Okay? So n should be S over r times n. Okay? For some integer S, and we will now think about what's the range of S. Obviously, S will be it should be from 0, 1 to r minus 1. Okay, because you cannot have a J bigger than n, right? Anyway, so we are basically done here. But we can be a little careful. Then we'll have, it should be right. So then what's the amplitude for each S? So go back. Okay. So we go back. So it's quite complicated. The amplitude of each J after you have sum over here. So this part for the non-trivial J will be n prime and equal to n over r. And we also have this part. This is some weird e to a 2 by jk over n. It depends on J, but if you take the absolute value, this is just 1, right? Because it's just some phase. So we do computational basis measurement, we don't really see this phase. Okay? And also interesting part is this is the only part dependent on k, right? So we can see that our QFT actually get rid of the k information. K information now only change the phase of our computational basis state. But we do computational basis measurement, don't see this phase. So previously, when we just measure this in computational basis, then this k gives us a lot of trouble. But then we do QFT, we basically get rid of this k information. We turn into some irrelevant dimension. Kind of, okay? So this part is just some phase, doesn't matter. So the actual amplitude is this n prime and this square root r over n. And so if you multiply things together, then that's 1 over square root n. And then you take amplitude square, that's 1 over r as you expected, because there are different a's. Okay. Okay. So yeah, we did what we expected. So if we normalize things a little bit, so we divide j by n, big N, then what you get is this phase is S over R with uniformly random distribution, just as before, where what we get from phase estimation. So, well, we're analyzing the same algorithm, so we expect to get the same result, but this is a different view. Okay, and the remaining question that we're going to brush over is this assumption, right? So assuming this pseudo analysis, assume n is a constant multiple of R, and we'll just say if you don't have that, then obviously things get a lot trickier. But that's basically where you need to do the equivalency analysis of phase estimation. Okay. And also all the computer friction things. Okay. So if n is not a multiple of R, then there are a lot of cutoff things you need to analyze. Say here you will have some weird cutoff, and also the summation part is not going to cancel out nicely. But because you are basically doing phase estimation, so the error analysis is going to be similar to the phase estimation error analysis. Okay. So you can work out that, but here we'll just leave it as like this. Okay. So we just claim that you can do similar analysis and show that the error will not give you too much trouble if n is not a multiple of R. Okay. So we are 10 minutes early. Anyone has any question? Otherwise, we think we can stop here. Or, I don't know. There are other things you want to say. Okay, I guess I can just show the whole thing once again. Okay, so this is what we do. Another view of Shor's period finding algorithm. So we are analyzing this phase estimation without thinking about the eigenstate of this one register. Right? So phase estimation is you start with your record register into equal superposition of everything. Then you apply your multiplication, so your control multiplication on 1. Then obviously you are going to get a whole bunch of x to the some power here. So the power k is just this k here from 0 to n minus 1. And then you do QFT minus 1, which will find out, so something we also find here is this QFT being plus 1 and minus 1 doesn't matter here, right? So because this minus sign doesn't naturally change everything, because if you do complex conjugate of everything, doesn't change. The input state is real and it's just measuring computational basis here. So you can have plus 1 or minus 1 here. Doesn't matter. And anyway, so we have this state and we'll do QFT minus 1. And let's see the number here. So before you do the oracle, you have equal superposition of every computational basis on the first register. Then you apply oracle, then on the second register you have this x to the kth power. And then we do this interesting analysis where we think about what happens if we do a measurement on the second register. So you do a measurement on the second register, then you are going to project this x to a k to one of the r possible values, because there are only r possible computational values. And if you project this to the value, then you will also collapse. Sorry, I should say collapse instead of project, although I am thinking about the same thing. Yeah. So you collapse this into one of the r possible value, and then you will collapse this k into the corresponding values. So that should be k, and so if it's some x to k here, the first register should be k or k plus r or k plus 2r, etc., all the way to k plus n minus r. And this kind of thing, we will think about Fourier transform is like a post-trend. It's equally spaced out signal. And you do Fourier transform, it give you another post-trend with with also equal spacing, but the spacing here become 1 over r. And I guess the real important thing is not so obvious fact, where you have a shift of phase trend of post trend here, right? So you are starting on k here, and this starting on k is a little annoying. It's very annoying on a computational basis. But once you do Fourier transform, then this shift to a k becomes some phase on the transformed post trend, as we see here, is just some phase. And so that doesn't change the location of those post trend when you measure in computational basis. And so that works out. So you measure this post trend, no matter what you k get, you always get this S over R results. Okay, and then you get S over R, then we go back to our. Then you can go back to our previous period finding analysis, where you draw a whole bunch of different S over R, then you take the LCD over the different R, then you can learn R, then you can do number theory to get your factoring. Okay. So we are about time. Okay, 5 minutes earlier. Anyone has other question? Otherwise, we'll just stop early. Okay. Then see you on Thursday. We'll go over ISA and probably something else.